Hello, my name is Soumik Sarkar. I'm a faculty member of Mechanical Engineering and Computer Science at Iowa State University. Today, I will discuss the role of interpretable machine learning in cyber agricultural systems. Let me begin with our vision of a sustainable cyber ag system that we are pursuing in various large-scale federally funded projects at Iowa State. Today, if we look at our conventional agricultural systems, as depicted on the left, especially in the US, we see large production fields, large capital investments, and large farming equipment needed for reasonable profitability. In addition, farmers are spreading chemicals indiscriminately, most of which is going to the water and river systems, causing significant pollution. With large farming equipment, we are also seeing significant soil compaction, and all these are making agriculture unsustainable. We want to fundamentally change this paradigm and develop a cyber agricultural systems framework. We want it to be scale agnostic, equipped with ground robots, drones, and remote sensing that can individually monitor and manage plants or plots. With such an individualized approach, the farm management, such as chemical spraying, will be ultra precise. This will also lead to minimal runoff and soil compaction. Overall, this should increase the profitability of agriculture and attract young generation to farming. Now, more precisely, our cyber agricultural systems to agricultural sustainability uh, involves individualized sensing, uh, modeling, reasoning, and finally, actuation. In all these steps, understandably, machine learning will play a big role. And my research primarily focuses on various aspects of machine learning as it gets applied to agriculture. Specifically, we work on robustifying machine learning systems for in-field applications, making these machine learning models interpretable, fusing multimodal heterogeneous data to extract actionable information, learning reasonably large models, such as deep learning models, with limited data, learning in a distributed and decentralized fashion with IoT devices, and finally, various decision-making algorithms. Today, I will discuss the need for interpretability of machine learning models and some of our recent success stories on this topic. Now, in the ML community, interpretability or explainability is defined as the notion of understanding why an ML model makes a certain decision given certain input data. Typically, high performance modern models, such as deep learning models, are black box in nature. That is, it is difficult to interpret its outcomes. And a large section of the ML community is okay with that. However, the other group in the ML community, and I'm very much a part of that, who work with science and engineering problems, where domain experts need to be convinced about an outcome from an ML model, can't ignore this aspect. Apart from building trust, interpretability may also lead to new scientific insights. So, with this thought in mind, in the problem described here, we wanted to build a deep classifier for plant stress identification, classification, and quantification, which is also interpretable. That is, we wanted to make sure that our model is actually looking at the stress symptoms in a soybean leaf image to identify and classify the stress. Now, in this particular case, we were able to show that. Here you see, three rows of images with the real images on the top row and our model interpretations in the middle row. We also asked some expert plant pathologists to mark the visual stress symptoms that they see in the leaf images. And they're shown here in the third row. We show that the model interpretations are quite similar to the expert markings, which really help generate trust among the experts in our model. The interpretations also helped us quantify the degree of stress level in an unsupervised manner. Now, model interpretability is not just for image data. It is also relevant for non-image data, such as time series. For example, in this case, we are very interested in building machine learning models for end-of-season yield prediction using weather data, genotypic data, farm management data, and so on. Such a model could be very useful both in breeding and production agriculture. Now, here is an example where we built deep LSTM models for predicting yield from multivariate time series data of weather. We also use some genotypic and soil characteristic information in this particular model. However, Along with good prediction performance, we are also interested in identifying important weather variables and time points in the growing season that the model is using heavily to generate these predictions. Therefore, in our deep LSTM model architecture, we carefully incorporated spatial and temporal attention blocks to answer these questions. Now, here are some preliminary results on a particular data set where the attention mechanism uncovered that average precipitation during about the middle of the growing season was key to accurately predict it. Now, let me wrap up with the disclaimer that while certain interpretability algorithms, such as the ones I showed here today, seem to be working for some models and for some data sets, the machine learning community is still far from the consensus on foolproof methods, especially for large nonlinear deep learning type models. In addition, the definition of interpretability is also quite subjective. It involves human intuition. So, still a lot research to be done in this space that can be deployed with very high confidence. With that, thank you very much for your attention, and I'll be very happy to take any questions at this point. Thank you.